There. Welcome everyone. Welcome folks on YouTube. Let's see if we are up on YouTube. I'll start it in a minute here. W3. Let's go here. And nope. Go. And we are live on YouTube. Okay, great. Welcome everyone on YouTube. Welcome everyone in the room. Today is the last Water, Wetlands, and Watersheds seminar of the semester. So we made it. Thank you all for coming today. And today we're going to end with the best of the entire semester. Yeah, so we have with us from the Department of Geological Sciences here at UF, Dr. Jorge Lorenzo Trueba. Jorge is an associate professor here, like I said, in geological sciences, and leads the Coastal Dynamics and Earth Modeling Laboratory, or CODIMO. CODIMO. His research uses mathematical and reduced complexity models to study how coastal landscapes evolve through shifting geomorphic and ecological boundaries, works across diverse environments, barrier islands, deltas, mangroves, and back barrier wetlands, and collaborates and seeking to collaborate more with ecologists, physical scientists, oceanographers, and even engineers and economists to examine how interactions between how people decide what to do with the land and how nature decides to respond affect our ability to live at the coast and the ecosystems that persist there. His work aims to clarify the mechanisms driving long-term coastal change and support resilient coastal management. So, perfect. Thank you very much.
Thank you. Thank you for the opportunity to come here and talk about my research with all of you. I have been here only for a little over a year, and I very much look forward to collaborations looking at the interplay between physical and biological processes at the coast. And I'm going to talk about a couple of examples that I think that illustrate that those kind of effects. One is on barrier islands like Long Beach Island in New Jersey, where in my previous institution is one of the barrier islands where I spent most of my time. I looked at this barrier island from many different angles, but one of them was looking at not only the barrier, but also the back barrier environment. So I'm gonna argue that this is a good example of a coastal environment where we can use a moving boundary approach to understand its evolution and what are the key processes that are driving change in this type of system. This type of work was funded by USDS, NSF, New Jersey Sea Grant. So I had more time to work on this. Mangroves is something that came a little bit more recently with a student called Isamar Cortez, and we were funded by NASA, and that allowed us to have access to some data. And what I show here is basically what we focused on. We decided to look at mangrove islands, like the ones here. All of these ones are in Puerto Rico, but they have an interesting shape. They have a donut shape with a salt flat in the interior. And from with my PhD, I actually started looking at islands and realized that there might be something interesting in the variability that you see depending on where you are on how these islands look. So, and stepping back for a second, just to tell you a little bit more about myself, I have applied the moving boundary framework to a number of coastal environments, including continental shelves, like the one along the East Coast of the United States. Deltas actually, where I started working on the moving boundary framework during my PhD and applying it to deltas like the Mississippi Delta. And now in my group, there is a student, a PhD student, Diet Bui, that is working on Arctic deltas, like the McKinsey. And today I'm going to be talking about barrier islands, like the ones that you see here along the Virginia Eastern Shore. Those are undeveloped. So here you see the names of all these islands, and in parentheses, you see the short-term and the long-term rates of migration. Some of the rates of migration of these islands towards land exceed 10 meters per year. So these are very rapid rates of migration. In contrast, we have barrier islands like Long Beach Island, on some of the islands here in Florida too, where you have a lot of development. And here in this image, actually, you see the shoreline protruding into the ocean. That's because it's just after a beach nourishment episode. These here, that is a little bit darker with, and actually has some vegetation that has been planted on it. These are engineered dunes that are 7 meters tall, 21 feet tall. So these are massive projects, right? So there is a big contrast in the way that these two type of barrier islands respond. Mangrove islands and reef islands is also something that I'm interested in, and I'm going to mention today. And also, I was mentioning before, beginning the presentation, that actually a student from my previous institution is going to defend this Friday to talk about some of the work that he did extracting coastal dune vegetation using drone surveys, including LiDAR, multispectral, and high resolution imagery. So if you're interested in talking about any of these coastal environments, I'm happy to talk about them. I will focus today on barrier islands and mangroves. And in terms of my research approach, so we use mathematical models, flume experiments, and all the field data that we can get. Flume experiments like the one here, this is a fluvial delta in a flume experiment at San Antonio Falls Laboratory, where I did my PhD. This delta was experiencing different wave energy conditions. This is, we actually had, as I mentioned, some drones in my previous institution. I plan to continue using them here. We also plan to buy some seismometers to deploy them on dunes and see whether we can get some information about the transfer of wave energy. But the core of my research is mathematical modeling. Quite often, even though I'm interested in models of all sorts of complexities, quite often we find ourselves developing simple models like the one shown here. This is a barrier island migrating towards land and the sea level rise. So these models, we build them to answer a specific research question. And the advantage of this type of model approach is that we try to minimize the number of parameter values that it has, because they are typically poorly constrained in natural systems, right? So the more parameters, the more calibration it requires. And sometimes if you are trying to understand the evolution over decades, you might compound those errors, and you might have problems to gain insight with higher complexity models. So what do I mean by a moving boundary approach? With that philosophy that I described in the previous slide in mind, what we do is to combine sediment conservation with an idealized geometry. An idealized geometry like the one that you see here, right? I'm sorry that it's actually reversed. That here we have the ocean in this case, and we go from the ocean to the mainland. This is what we probably would see if we take a cross-section in Long Beach Island here, right? So if we take a cross-section along Long Beach Island, we would go from the shore-face toe, which is underwater, and is the depth beyond which you don't have any significant sediment transport by waves. And then we have the ocean shoreline, we have the bay shoreline, the marsh lagoon edges, the marsh mainland edge. If we can write down the rate of change of each of these geomorphic boundaries as a function of the key processes that drive change, like sea level rise, overwash, which is bringing sediments from the front of the barrier to the back, and that's how barriers are able to keep pace with sea level rise, or sediment transport at the surface between the upper and the lower surface. If we can write this, or biological processes in the back barrier and the bottom, right? Wave energy in the lagoon, organic sedimentation, all those processes can contribute to the change of these geomorphic boundaries. And here there is an example of a model developed few years ago, in which the barrier, not only the barrier, but the barrier and its associated back barrier environment is migrating towards land, as you would expect under sea level rise. The overwash fluxes are allowing the back barrier marshes to be maintained, and this is what you would expect under undeveloped systems, right? Okay, so then now that I had the opportunity to introduce what do I mean by moving boundary approach, let's go over 3 different examples in which I think that there is, well, we can learn a lot from applying a moving boundary approach. The first one is looking at Long Beach Island and specifically ask, what is the relative role of coastal engineering on the evolution of this island over the last couple hundred years? And then we will move into mangrove islands and move into part 3 to look at higher complexity islands. The really underlying question for the mangrove island section is, what is the role of the net evaporation rates on the way that these islands look, their geometry and their extent? So coming back and zooming in into the Virginia Eastern Shore, just to make the point again of how barrier islands, how dynamic they can be. Here you have Cedar Island, how it looks in 1984. And this is what the shoreline looks like at that time, more or less, roughly. And this is the island in 2016. So the island has rolled over itself a few times and has undergone a rate of migration that exceeds 10 meters per year. 10 meters per year is quite high, I think. So they are arguably among the most dynamic coastal landscapes on Earth, right? But of course, that in contrast with areas like seaside heights that are heavily developed and have been fixed in place for a few decades, right? So in the case of Long Beach Island, what is the role of hard structures like groins here that you see on this slide, perpendicular structures to the shoreline that are aimed to trap sediments from the alongshore current, or beach menaces, like the one that I mentioned before. So we are going to use the idealized geometry that I presented before, and we are going to collect as much information from historical maps as we can and try to look at the change of each of these geomorphic boundaries during this time period, okay? And this is an example of some of that analysis with historical maps from Kristen Russo and Shane Nichols. So I guess that the main point that I want to make here is that we don't have historical maps that we can use every single year. We are limited by how much of these historical images are available, and the farther back that you go in time, the more likely you are to have some error too. So we try to take that into account, but we are limited as well. But you can actually learn a lot, right? And here, for example, in Island Beach, just north of Long Beach Island, we can see the areas where we have accretion in green or erosion in yellow. Here we see the growth of the spit in the south, but a lot of erosion in the upper portion of Long Beach Island. That's the type of work that we did. And now, if we take the average alongshore, this is what we learn. This is one of the things that we learn in Long Beach Island, is that roughly you can separate the evolution of Long Beach Island in 2 phases. One from 1840 to the 1930s, roughly, in which the entire barrier marsh lagoon system is migrating towards land. All geomorphic boundaries are migrating towards land, as you might expect from under sea level rise. But after the 30s, with beach management practices and coastal engineering, after losing the lighthouse a few times and saying, okay, we need to do something about this, you see that in the geomorphic change that this barrier experiences. Then the shoreline doesn't migrate towards land, actually grows seaward, and that has happened in a number of islands in New Jersey, probably in Florida too, and back barrier marshes eroded and actually are fully developed. So now we basically lost the back barrier marshes in reality, but even before we fully lost them, they were eroded because they were not getting overwash sedimentation that helps to maintain them. And the inland marshes eroded on the lagoon side, and actually in the inland side, they were lost to development. So that's what we call coastal squeeze. We were basically losing area from both sides. So I would argue that this type of work can help us to, if now coastal communities in Long Beach Island or some other similar barrier island decide to not nourish that much, or for different reasons, because the cost of sand is higher, because of the loss of appetite from the federal government to subsidize this type of projects, or etc. I think that having a benchmark on how the barrier was migrating before, I think that is important, because that is what can help us to project and try to, under different scenarios of development, how is this barrier going to evolve moving forward, and the different levels of coordination or under different socioeconomic conditions. And a lot of opportunity, I think, to this type of approach. I think that's portable to Florida, right? Now, part two. In part two, we are going to, let me give you actually a little bit of background. So, as I mentioned, I was working on deltas during my PhD, and the idea was to also look at some of the islands that form within deltaic systems. And I realized later, I started working on some other directions, but I realized that maybe it would be better to look at islands that are not affected by river sediment supply or sometimes development. And why not looking at remote islands that are in many cases in the middle of nowhere, growing on a carbonate platform, right? Because then it's a much better place to look at a specific question like, what is the role of net evaporation rates? If you also have freshwater inputs and you have sediment supply coming from the river or other things, it's more difficult to answer that question, right? And after looking at Google Earth for a few, it's kind of addictive, but I realized that mangrove islands can look actually quite different depending on where you are. And some are, when I was then a Montclair, came to my office, I would like to work, do you have something that I could start working on? And I said, are you interested in building a mangrove island data set? And she's from Puerto Rico, so she actually, I think that she was very interested because she had seen mangroves and that La Barguera Bay that I will talk about later. So she collected the information from mangrove islands in all these different Belize, Mexico, Florida, Bahamas, Cuba, Puerto Rico, Venezuela. And the first thing I did is to just with Google Earth Engine, just to map what the geometry looked like and what is the vegetated area for each of those islands. And then we realized, well, let's go farther and see we get a sense that, yeah, we know that in Belize, precipitation and evaporation is more balanced than in places like Puerto Rico, where you have higher evaporation rates compared to precipitation. So let's see if that tells us something about these differences that we see between the islands. So she gathered information from the Tropical Rainfall Measurement Mission that started we had data from 1998. That's why we use this one as opposed to the more newer data that we have. And then evaporation data from the OFLAX project, that was Oceanographic Institution. And the time window overlaps is, we used, I think at the end, 1998 to 2019 or 2020 or something like that. And we just took the average and said, let's look at just the average, the net evaporation rate that characterizes each of these regions. And that's what you see here in the plot here. And we then put together the vegetated area for these different islands as a function of net evaporation rate, the net evaporation rates that you see in the plot on top. And yeah, there is maybe some kind of trend. And it's like, okay, yeah, so there are lighter.
Okay, is the vegetated area scaled to the overall area, or so like, just if there are larger and smaller platforms, like this is included in this, right? It's like the gross aerial measurement of the island size distribution is.
Good question, really good question. So the only place where we saw mangroves extending to the full extent of the carbonate platform is in Belize, which I think that illustrates the fact that in Belize, and sometimes you can have salt flats, but that is sometimes even a seasonal thing. But in the rest of the places, we don't see as much of a control. That doesn't mean that there is no control effect, bathymetric effects, which we don't know.
Okay.
And that could actually be maybe something that is a part of the story in Florida. But many of the islands, even though they look irregular, there are other mangrove islands next to them. So the carbonate platform is not because there is a very deep location right after them or something.
Right. Okay. So it's like you think it's like a biogeogenic process?
For at least some of the islands, like this one, for example, here in Belize, there are a couple of Smithsonian places. So we try to read a lot about what is happening in Belize. Those are the shape of these mangroves is fully dictated by what the carbonate platform looks like.
Yeah.
But the only place I think that is Belize, from what we gathered. So net evaporation rates are not the full story. What else, right? And we said, well, let's not go super complicated. Let's just add one more process. Let's try to incorporate the ability of these islands to flush out the salt from the interior. And no need to really go into the details here. This equation is just a dispersion equation with a source term. This term is basically telling me that net evaporation rates are playing a role, right? So this is what is, and I should have explained why net evaporation rates affect the way that the vegetated area happens. Because if you have evaporation exceeding precipitation, you are removing the water and leaving the salt behind to a large extent, right? So what that means is that in these islands, typically what you see is an increase in the salinity as you go toward the center. So you might have salinities maybe 35 parts per thousand in the outside, in the perimeter of the island. In the interior, and this is something that in Puerto Rico, when I went for the first time, if you have visited, you see hypersaline lagoons that can be,
70, 60 pt.
And sometimes higher, right? In some of these cases, I think that it probably exceeds 100 parts per thousand, because the threshold for black mangroves to grow is in the order of 100. And what we see in some of these islands is a transition from red to black and die-off, which suggests that we are probably exceeding even those levels, right? So this is the salt concentration profile that I can quantify using these equations, right? And this equation has the dispersion coefficient on this term is just a way to explain the ability of the island to flush out that salinity. And there are a bunch of processes that can be part of this dispersion, but this dispersion accounts for different. So if for the same net evaporation rates, and the same outer edge salinity in an island, you see differences in the vegetated area. Maybe it's because of differences in this dispersion coefficient, which might include grain size or soil characteristics of different kinds, etc. Right? And the simplicity of the model allows us to, just express the salinity concentration profile just with this quadratic here. So, and the key ingredients are here: the net evaporation rate, the outer edge salinity, which is the boundary condition, the salinity at the edges of the island here, and the dispersion coefficient here in the denominator. And using this model, we can say, oh, well, the vegetated area then can be, assuming a circular island, can be expressed like this, as a function of the dispersion coefficient, the outer edge salinity, the net evaporation rates, and this critical threshold for vegetation to grow. So simple, but very clear relationship, right? So now, how do we want to compute what is the vegetated area for each of these islands? We need to estimate each of these parameter values. How do we do that? Because this part of this project happened during COVID, but even if we had, funding, I mean, we cannot go to every single island, and they are remote islands. So we had to use remote sensing, right? And this is, I think that our first try to compute the dispersion coefficient, which I think that is really the most difficult one, right? Because it encapsulates so many different processes. And what Isabel and I decided to do is well, how about we, based on the modeling framework, we could express this dispersion coefficient as a function of the area of red mangroves. So what does that tell us is that if we have an island that, again, under the same net evaporation rates, the same outer edge salinity, we see differences in the area of red mangroves, that means that the island with larger area of red mangroves is doing a better job flushing out that salinity. Because otherwise, we would see a transition to black mangroves and die off, right? So that's what this diagram is trying to represent. So we have the reference here with the transition. The red mangroves are in dark green, and then the black mangroves in light green, and then they die back in white. If we increase the dispersion coefficient, that is the ability to export the salt outside, then we are going to increase the area of red mangroves. And if we increase it even more, we have even more red mangroves in our mangrove island, right? But how do we get the area of red mangroves? Well, because luckily we were funded by NASA, we had access to PlanetScope, high resolution imagery that including near infrared. This is what the color composite looks like for some of these islands. And combined with a random forest classifier, we were able to separate red and black mangroves. And that's what you see here in the output on the bottom. Red mangroves are in red, black mangroves in black. So to first order, we can compute what the dispersion coefficient is. So now, coming back to what really this model is very simple. We have three key parameters that we need to estimate. Net evaporation rates that we get from satellite information. We have the dispersion coefficient that we estimate based on red mangroves, and the outer edge salinity, which we said, okay, we don't have information. There might be some ways that we can estimate, but let's assume that in all islands is 35 parts per thousand. Let's see how much the dispersion coefficient can add to the story, because we know that net evaporation rates are not doing a satisfying job. And just to give you directionally the effect of each of these different processes. So net evaporation rates, the higher the net evaporation rate, then the more the higher the curvature of the soil concentration profile, and the larger the likelihood, the higher the likelihood that you are going to exceed the threshold concentration for mangrove growth. Dispersion coefficient, the higher the dispersion coefficient, the lower the curvature of the soil concentration profile. And the outer edge salinity is not affecting the curvature, it's actually shifting the profile up and down, right? Because it's the boundary condition, right? So the higher the outer edge salinity, the profile shifts upwards. So what do the results look like? This is the vegetated area computed from the model in the vertical axis, and this is the vegetated area obtained using Google Earth Engine and mapping it by land. Isamar did that, right? And we were actually very happy to see this. We saw a lot of the islands falling on the 1-to-1 line, or close to the 1-to-1 line. Of course, this is a log scale. And yes, there are some outliers, but it's better than what we had before, which is telling us that there is something to the dispersion coefficient. It's adding explanatory behavior, explanatory power here. Interestingly, though, most of the islands that are not outliers here are in Florida. So that's great, because that means that there is a lot of work to do now that is on our backyard, right? So, and these are some of the islands here in Florida Bay in yellow that were included in this analysis. And of course, one of the first things that jumped to us is that, well, the assumption of the outer edge salinity being 35 parts per thousand here in a bay doesn't hold, right? And that's something that we touched on briefly. Of course, in the this is I'm sorry that the numbers are very small, but here the point is that there are a lot of seasonal changes, but also the range of salinities can go all the way from 25 to 45 parts per thousand, right, or more, right? And so what we did is okay, let's distinguish the islands depending on where they are located in the bay and see whether that might be a contributing factor. And yes, the outliers where the model is under predicting the vegetated area happen to be islands that are in a section of the bay where outer salinities are lower. So that is not the whole thing. There is something else, because that alone cannot explain the differences. But it's something to start with, So I'm excited to maybe see how we can improve this type of approach. And but if you agree that this model can do a fair job explaining the differences in vegetated area in mangrove islands across the Caribbean, then that means that we get a relationship between vegetated area and net evaporation rates that we can use to project into the future. So assuming dispersion coefficients and outer edge salinities are constant over the next few decades, simply because we don't have information or we don't have a good guess to project, what would be the vegetated area change associated with only net evaporation rates? And we use the climate change knowledge portal, where they have different global climate models, and we have, but we took the average of the three models that they had, and then you look at different pathways from the IPCC, right? And in general, what we see is that there is going to be presumably a substantial mangrove loss in all cases. And but it's also variable. It depends on where you are. So there are places like Belize where they have more to lose, right? Because they are starting from a net evaporation rate that is close to being balanced, but it's gonna increase. And if they have large mangrove islands, it's much easier to create those salt flats in the interior, right? So, and areas like Venezuela and Mexico are also disproportionately affected by this, according to the global the climate models that we have today, right? So all this is assuming islands that are circular. Now, I just have a few slides to show you some work that is not published yet, but is work in progress. Isamar and I are working still on this, trying to extend this model to account for some of these geometric complexity in the geometry of these islands. And this is, by the way, not the weirdest island I've seen. I mean, there are islands that definitely require, you know, a little bit more than just a circular, right, assumption, right? So, and to start, we focus on La Parguera Bay, where, you know, my interest in mangroves, I think I started when I went to visit there for fun, and I saw the bioluminescent algae in one of these canoe tours, and it's when I learned about the hypersaline lagoons, and I saw the mangroves, and I thought it was fascinating. So, and in those bays, you also see many of these mangrove islands. And what we what caught our eyes that here in this bay, we can separate into a primary bay and a secondary bay. The islands that are facing the primary bay look like this, and the islands that are in the secondary bay look like this. There is maybe a subtle but noticeable shift of where the die-off happens closer to the secondary bay. Apart from the fact that they are, of course, elongated and they have a more complex shape, but the secondary bays don't have that, right? So we were wondering, what can we explain that shift with the parameters that we have in our model, the dispersion coefficient and the altered salinity? So we just extend, this is the same equation I showed before, but now we have both the X and Y directions, and we have a dispersion coefficient that is a function of space. The net evaporation rate is going to be the same because the resolution for the net evaporation rates is 100 kilometers anyway, so we don't have the resolution to look at different spatial variability, but the dispersion coefficient or the outer salinity, we can make it a function of where you are on right. So here in this case, this island that is facing the primary bay, we see a salinity in the primary bay that is slightly lower than in the secondary bay, right? And also for the dispersion coefficient, that was our hypothesis. Maybe this is something that we can explain by accounting for this spatial variability. And the secondary bays, we go back to the symmetric case in which there is no spatial differences. Well, let's see if that can be is supported by the data, right? Now, we actually we contacted people in Puerto Rico, we tried to get information about salinities in the bay, but they only have one monitoring station in one location in the entire bay. So we cannot separate what the salinities are in the primary bay and the secondary bay. But what we thought that it would be an indirect way, but with potential approach is to use canopy heights, because also through NASA, we had access to GLI data, and many of these islands were covered, were part of the flights that were used to collect this information. So, and this is the one example of what this LiDAR information looks like. We can use it to quantify canopy height and put it together with work that Edward Castañeda, Robert Tweedy have been working on for a while, and see whether we can infer from the canopy height what is the salinity in each side of the bay. And this is what so here we have canopy height in the vertical axis, we have salinity in the horizontal axis, and the red corresponds to the secondary bay range for canopy heights that we extracted from GLI, and the blue is the range for the primary bay. So the difference is not that, right? So there is something else going on. Good try, but something else has to help. And we use the same approach for the dispersion coefficient to see whether that could add value. So instead of using the red mangrove area for the entire island, we split the island in two, and we calculated red mangrove area on the side facing the primary bay and on the side facing the secondary bay. And indeed, we see, and no need to worry about the numbers here, but there is 2 points I want to make here. One is that indeed there was a difference, higher dispersion coefficients on the side facing the primary bay than the secondary bay. And the values are within the range of physically meaningful values that we found in the literature. Granted that the range of values for dispersion coefficients is quite large. But if we use these inputs, and now what is the output of the model, and how well can we do in explaining the dieback? And you see all the second row here are the model results. And the dark gray is the dieback. So we are not doing a great job, but we think that we are capturing a little bit of that shift of the dieback towards the secondary bay in islands like this one and this one, and some of the complex geometries that we see, right? So still a lot of work to do. And this is my last slide, just to wrap up that even though we really didn't, moving that boundary approach means that the boundaries are moving. Some of you might say, oh, well, you used a model for the mangroves, but it's not really a moving boundary approach because it's not moving. That's where we were going towards, because what we wanted to do is to account for the expansion and contraction of these salt flats that, but it's very difficult to gather information about this because of the lack of information, right? But that's where we are going towards. And if we have specific islands where we can go and collect data in situ, I think that there will be. And I want to also highlight that this type of model approaches, even though simple, they can be extended, they are versatile. So for example, in the case of barrier islands, some of you might not be very satisfied looking at a barrier island in cross shore, right? But this is also another, modeling effort, and I forgot to here put the citation, but it's some work from Jack Milhouse and myself looking at connecting those cross sections together with an onshore sediment transport. So what you're looking at here is the barrier island migrating towards land and these different inlets migrating down there. So depending on the question that you are trying to address, you can use one model or the other, right? But if we apply these models to learn what are the key processes that are driving change, I think that we are better positioned to project into the future. So that.
All right, thanks. Let's give a round of applause. Nice, the lab that eats together is a happy lab. Yeah, that's great. So we'll go for some questions in the room. First, questions from students in the room, and then I'll check YouTube. So just a couple of students, but spotlight's on you guys first.
So maybe someone else wants to ask first.
Okay, we'll open it up to anyone in the room. So nothing on YouTube yet.
So if you're interested in a system completely different but similar to your mangroves, suggest you look at the Okavanga Delta in Botswana, which is a distributary. It's fresh water, but it produces all of the characteristics that you're getting, and there's competing explanations of what's going on there, but it would be a beautiful sister corollary to your mangrove stuff.
Yeah,
And
that's
I've got connection, very good connections
Oh.
there, so.
Yeah.
great. Yeah, so
And they're interested in what's going on with this design.
They form circular patterns, the salt has to go somewhere, because it's all evaporated, it's a freshwater, but then the salt is sort of like cryptically gone, and they think it's transported with these density gradients, and so, yeah, it's a lot of
A lot of
similar
really
sort of
cool stuff.
structures, yeah.
Really cool stuff.
I'll reach out, and I will say that I mentioned that some of this started in my PhD looking at deltas. We were looking at the Fly River in Papua New Guinea, in that region, and I think that they also have mangrove islands there that I think that there might be some overlap with.
This is in the middle of the Kalahari Desert, so there's no salt, there's no mangroves, but
Right.
it's really, really interesting. It's all fresh water, but it generates this high salinity.
Okay, we have a question from Dr. Anna Braswell. She's in FF Bars. She's at UF, and she asks, have you thought about some of the same evaporation dynamics in salt pans and salt marshes in the southeast? So not in mangroves, but in sort of, the same sort of zonation occurs in the high tide zones that are infrequently flooded, but they hyper concentrate salts in the same way.
I would be not enough. I didn't think about those enough. So I would be very interested in talking with you more about that, Anna. So in terms of whether this model approach is portable and can be used, I believe so. Because I think that the thresholds for, mangroves are salt tolerant and more salt tolerant than many other some other vegetation that you can find in coastal wetlands, but there is a lot of portability there. So
go ahead.
Are you familiar with petenes?
Petenes.
In the Yucatan Peninsula, you have petenes, which reminded me of this island, mangrove island. But instead of having these areas without vegetation, they have a spring in the middle of the island. So, and these are all around, not all around, but the western and northern coast of the Yucatan Peninsula. So in that case, let's call it deforestation is not caused by hypersalinization, but by freshwater output, I guess. So I wonder if there could be any connection.
That's a very good one. Yeah, sorry.
Yeah, no, I also have questions about your model, but maybe I could stay. If there are more questions, I could stay at the end and discuss them.
Yeah, so, but groundwater is something that we try to do selecting the islands. We try to select islands that were try to make sure that they were the only freshwater inputs that they were getting is from precipitation to the best of our ability. But it's true that in some cases groundwater connections could actually, but how close are those islands to the mainland in that case?
They're within lagoons sometimes.
Yeah, so that I think I can see that there is some seepage, some groundwater flows that would actually
yeah, that changes the direction of the discharge changes with the tide. So that's another aspect that your model disregards tide for.
Well, and they are, and that's very interesting because there are mangrove islands on the Pacific side, and we disregard tides because we take. And I do that. In order to have tides, we will have to have an advective term there, right? But if you just as grossly assume that the dispersion coefficient, increases if you have more higher tides, you could. But we are looking at all the islands that we are looking at are in the Caribbean, where pretty much everywhere that we looked at is microtidal, right?
Right, but still you have flooding and drying. Even the tide is like this much.
Yeah,
Or it could be
and a very
more.
low line, very
Well,
low
yeah.
line
You'd still-
environment, so it still is something that we need to start, finding ways to take into account, yeah. So it was a gross assumption to start with, but and the way that we were thinking as well, if we to first order, if we want to, and we actually did some analysis trying to see whether wherever there is a little bit more higher tidal range, are we over predicting or under predicting vegetated area in those cases? And we looked at that, but that's definitely a direction that if we want to apply the model to a very particular location, like in Florida Bay, then I think that those are things that we need to go more in detail, I think. So, good point.
All right, and we have time for maybe one more question from YouTube, which is, so given all these dynamic processes, do you think that a moving boundary approach might help inform more sustainable planning and permits, since decisions are usually based on some sort of fixed delineation?
Yes,
Yeah.
I truly believe so, and I was trying to think about examples where there are so many, right? I mean, understanding how a system before you have, before development or before anthropogenic effects was responding and put it in within the context of the key drivers, I think that can definitely inform decisions. And one of my students is actually working on dunes. I didn't mention him, but he's developing a burn dune model, but accounting for habitat for shorebirds. And so there is a lot of opportunity to use this type of frameworks for conservation too, especially when you want to look at decadal time scales, right? When changes in the landscape become important, right? And at the same time, we want to make decisions. Many of the decisions that we make as coastal engineers, right, or as in terms of hard structures or building a road, we are thinking about decades ahead, right? Even if you're in a state park, right, you have to build those roads that you hopefully are going to have there for a few decades, right? So yes, there are decisions there that I think that could be you could get some
Insights
help,
from
some
that,
insights
yeah.
from this type of approach.
So let's give another round of applause to Dr. Lorenzo. Thank you. Okay, everyone, so that basically completes the semester. For those of you who are taking the course, I don't know how Dr. Clark's doing. I'm about 3 weeks behind on abstracts, but we'll get them in very quickly. Once I get your abstracts graded, then I'm going to bug you about the course evaluation. Probably that's the good order to do it in. But I really appreciate everyone in class, online. Thank you, Billy and Lisa. You're always there on Zoom, and everybody on